The energy equation provides a useful relation between the distance to the central body and the magnitude of the velocity of the orbiting body. Let us find an additional helpful relation. We start once again with the equation of motion. This time, however, we shall multiply it as a cross product with r, obtaining this expression. Clearly, the gravity force is a central force, so the term on the right-hand side is along the r direction. Therefore, its cross product with r is equal to 0. Regarding the left-hand side, we can use the following identity to rewrite it. In this identity, we clearly see that the second term on the right is 0. Hence, if we integrate the resulting expression, we obtain the following final result. Here, h is the angular momentum of the satellite about the central body, and we see that it is another conserved quantity of the motion. Since the component of the velocity that matters in the definition of h is the one perpendicular to r, we can make use of the angular rate dθ over dt to write the magnitude of h as this. And therefore, this expression tells us that the larger r is, the smaller the angular rate becomes, and vice versa. As a result, the tangential velocity is larger at the pericenter, that is, the point of closest approach to the central body, than at the apocenter, the point of largest separation. Indeed, our simulation shows this effect. Moreover, the conservation of h is what demonstrates that the motion of the two-body problem is planar. Since h is perpendicular to both r and v, and h is a constant vector, r and v have to lie always in the same plane. We call this plane that contains the whole motion of the satellite the orbital plane. Finally, at this point, I would like to tell you about the laws of Johannes Kepler, the famous German astronomer of the 16th-17th century. Based on the observations of his master, Tycho Brahe, Kepler established empirically what the planets move around the Sun in elliptical orbits, with the Sun at one of the foci. He also noticed that each planet sweeps the same area per unit time, as seen from the Sun, regardless of its position in its orbit. This, in fact, is a natural consequence of the conservation of the angular momentum. Indeed, the area rate is given by the area of the elemental triangle of the figure swept in an infinitesimal amount of time. This rate is given by this expression over here. Clearly, using the definition of h, we can write it like this. And therefore, the area rate is constant. Lastly, his third law states that the square of the time it takes a planet to complete one orbit about the Sun is proportional to the cube of the semi-major axis of the ellipse. Again, it is possible to derive this result from the conservation of the angular momentum. To conclude, it is worth to emphasize that in essence, Kepler's laws are purely empirical and based on observations. The three laws of Kepler can be derived directly from the laws of Newton and Newton's law of gravitation.